So, in the last lecture we finished the proof of Dirichlet's unit theorem. Let me remind you what Dirichlet's unit theorem says. It says that the units in ring of integers of a number field is a finitely generated abelian group. Moreover, it gives rank of the free part in terms of the number of real and complex embeddings of the number field. So, we proved two important theorems. One is finiteness of class group, another is Dirichlet's unit theorem. And we want to do computation. So, we want to be able to compute rings of integers, we want to be able to compute ideal class group, we want to be able to compute the unit group. And for that it is important to understand how primes, rational primes factorize in a number field. And as I told you last time, it is no more difficult to consider how primes in one number field factorize in another number field. So, this is what we are going to concentrate on for the next few lectures, on how primes behave when you take them in a bigger extension. Okay. So, how you change things. Okay. So, here is the setup. So, let F be a number field and let K be a finite extension of F. Okay. So, usually I like to denote this in terms of a diagram like this, right. So, K is a finite extension of F. So, here is a piece of notation. Okay. Let A be an ideal. Okay. Then we can do then A times OK is an ideal in OK. Right. So, this is what is sometimes called, co-norm of A. Okay. So, co-norm in this relative extension K over F, but I am simply going to denote it as AOK. You can also call it extension of A to K. Okay. All right. But in any case, I will just denote it as A times K. So, this is how you start with a ideal in a smaller number field and then get an ideal in a larger number field. So, on the other hand, let B be an ideal. Then there are two ways of getting an ideal inside OF from B. So, you can do B intersected with OF. This thing is an ideal in OF, or you can do norm from K to F of B. This is also an ideal in OF. Okay. Let me remind you what norm is. So, norm from K to F of B, this is equal to norm of each element. So, okay, let me actually write it in the following way. So, this is ideal generated by norm from K to F of x for each x in B. Okay. So, you take norm of each element from K to, so norm of each element in B, and that gives you a subset of OF, and you take the ideal generated by that subset. Okay. So, that is what norm of B is. We have seen this before. This is just a reminder of the definition. Okay. So, if you start with an ideal in a bigger number field, there are two ways of getting an ideal in the smaller number field. You either take norm or you take intersection. Okay. But if you start with a ideal in the bottom field, then generally there is only one way of getting an ideal in the bigger thing, which is you just take the ideal generated by A in OK. Okay. So, that, and we denote it as A times OK. Okay. All right. So, we will study how properties of these ideals as you go up or you go down, but here is a curious lemma that I want to tell you first about. So, here is a lemma. This is true in Dedekind domains, but not in general. So, let F be a number field and beta be an element in OF. Let A contained in OF be an ideal. Then, maybe let me state it. If beta to the n belongs to A to the n, then beta belongs to A. So, this is very curious because I am saying that beta to the n belongs to A to the power n. This is for some n, for some n bigger than 0, some integer n bigger than 0, then beta also belongs to A. And the reason I say this is curious is this is not true in general for any ring. You can have nilpotent elements in a general ring, and for a nilpotent element some power is 0, so it belongs to every ideal, but that does not mean that this element will belong to necessarily belong to every ideal. Okay. So, and the proof is simple, although it uses this powerful thing we proved about Dedekind domains. Okay. So, it is enough to do this for prime ideals, right. Yeah, let me say the following. It is enough to consider A equal to P to the power m for some m bigger than 0. Okay. And why is this enough? Because if if beta belongs to P1 to the power m1 and beta belongs to P2 to the power m2, then beta belongs to P1 to the power, and P1 and P2 are distinct, then it also belongs to P2 to the power m2, right. This is Chinese remainder theorem, if you like. Okay. All right, and you can extend it to finitely many distinct primes. So, it is enough to consider the case when A is a prime power. All right. So, what you do is you consider the ideal generated by beta. Okay. Now, this will be equal to P to some power k and then some other ideal. Okay. So, for some ideal B co-prime to P. We can always write it in this way. Okay. So, B may be trivial ideal, I do not know a priori, K may be 0, I do not know a priori. Okay. And A, of course, is p to the power m, right. Now, what am I given? I am given that beta to the power n belongs to a to the power n, which means that the ideal generated by beta to the n is contained in the ideal generated by a to the n, I mean the ideal a to the n, right. But what is this ideal? This is p to the power k n times b to the n, okay. And this thing is contained in p to the power m times n, right. This is equal to this ideal, all right. But b is co-prime to p, that's how we constructed our b. This means that k to the power p to the power k n is contained in p to the power m n, right, which means k n greater than or equal to m n, but n is non-zero, and so k is greater than or equal to m, which means that the ideal generated by beta is contained in A, which means that beta is in A. So, it is a curious little lemma that turns out to be useful, and it fails in a general ring. It is very peculiar to Dedekind domains, and something that is very peculiar to a particular kind of ring is usually, even though it is easy, it should be considered interesting in my opinion. All right. So, we can use that lemma to prove the following proposition, going back to our original theme. So, let k over f be a finite extension of number fields. Since they are both number fields, I do not really need to say that it is finite extensions. Both k and f will be number fields. So, they will be finite extensions of q, and so k over f has to be finite, but nevertheless let me put that redundant word in there. Let k over f be a finite extension of number fields and let A be an ideal in OF. Okay. So, now I can extend A to an ideal in K. So, I get an ideal in K, and then I can look at intersection, and you can ask what is this ideal, and perhaps unsurprisingly this turns out to be A again. Okay. We will see later on when we do computations that this is no longer true about norms. So, if you extend your ideal A to an ideal in K and you take norm of that ideal, it need not be A. It will contain A, but it will, in general, it can be bigger. Okay. So, how do you prove two sets are equal? Generally, the strategy is to show that one is contained, first one is contained in the second, and then the second one is contained in the first. Okay. And as is often the case, one inclusion is easy. So, here the easier inclusion is that A, the right hand side is contained in left hand side. So, let x belong to A, then x times 1 belongs to A times OK, right, and hence x belongs to A OK intersected with OF. Okay. Therefore, A is contained in A OK intersected with OF. Okay. So, this is the easier inclusion. The other inclusion is not difficult, but it requires the lemma that we proved before. So, let beta be an element in A, O, K intersected with O, F. Okay. Therefore, we can write beta as summation over I. So, I going to over some finite thing, okay. This thing in A, O, K. So, what are these? Alpha i's, these are in A, and xi's are in OK. Okay. So, this is you can write it as a sum like this on account of beta being an element in A times OK. Okay. All right. Now, if I take beta, well, let me write it slightly differently. If I take norm from K to F of beta, this will be equal to beta to the n, right, as beta belongs to OF. Right. If you take norm of some element which is actually in the bottom field, you just raise it to nth power. Okay. On the one hand it is this, but on the other hand you can write it as norm of K over F and then summation alpha I xi, right. Okay. So, how do you write norms? How do you define norms? We define norm as product over J. So, J varies over all embeddings of K into complex numbers that fix F, okay, sigma J and then summation alpha I xi. Okay, so, this I has nothing to do with J, and I can rewrite this as product over J summation alpha I sigma j of xi, right, because sigma j is a embedding of K that fixes elements of F and alpha i's are elements of F. Okay. And so, you see that this is contained in A to the power n on account of the fact that you can write this as symmetric, right. You can write this as a polynomial in alpha to the I with coefficients that are given by symmetric functions of xi. So, these functions are in OF, and then it is a homogeneous polynomial of degree n. So, okay, let me this is equal to homogeneous polynomial of degree n in alpha i's, right. What is n here? Sorry, I should have said here n is degree of K over F. Okay. All right. I hope I did not use n for the, yeah, I have not said what I varies over. I is just varies over some finite indexing set. So, this is a homogeneous polynomial of degree n in alpha i's with coefficients in OF, yeah, okay, and therefore, this is in A to the n. Okay. All right. So, we have proved hence beta to the n belongs to A to the n. Therefore, beta belongs to A by the previous lemma. Okay. Alright, so we have proved the lemma that if you take an ideal in the smaller number field, extend it to a bigger number field and then take the intersection with the smaller number field, you get back your ideal. So, actually we have proven in the proof we just use the following. So, here is the corollary with the notation as above. If you if you take this, then this is also equal to A. Okay. We did not use that intersection, we are taking intersection with OF, we just needed that we are taking intersection with F. Okay. All right. So, here is here is another lemma, or let me write it as a proposition. Right, okay. Yeah, let me find the right way of stating it. Okay, so okay, so before doing that we need a bit of notation. All right. Yeah, okay. So here is a bit of notation. Right. So let L over K over F be finite extensions of number fields Okay. So, in terms of this tower of number field, it will be a tower like this, right. So, K is a finite extension of F and L is a finite extension of K, and consequently consequently L is a finite extension of K, but we also assume that L over F is Galois extension, right. Then we can do the following, right. So, we can okay. We can take right. Let B be an ideal in K, okay, and A equal to norm from K to F of B, right. So, so B is contained in here, A is an ideal in here, and what I am saying then is that if you extend A to L, this is same as product overall sigma i's of extending sigma I B to OL. Okay. All right. So, this is the way to write it, right. So, what I am saying is that Yeah, so what, okay, let me tell you what the motivation of this proving this proposition is. We define norm of an element in terms of product of embeddings into an algebraic closure, right. So, this proposition is going to help us prove the same thing for ideals. So, let us take the case when L is equal to K. Okay. So, we can always take the case when L is equal to K, right, and then or maybe, yeah, sorry, let me take the case when let me take the case when K is equal to F. Okay. So, there is only L over F as an extension, then there is no business of norm here, and what this is saying is that sorry, I am confusing myself and you, I guess. So, I want to say that norm of from L to F is given by product of embeddings. Yeah. So, let me write it on the next page. So, remark, if L is equal to K, then norm from L to F of this ideal that that we denote by that we denote by B. So, I can take this as an ideal of OF, and when I extend it, this is same as product overall sigma I of B. Okay. All right. So, this has very similar flavor to what we know for norms of elements. All right. So, how do we prove this? So, this is somewhat tricky to do, because there are so many, there are two extensions involved, right. So, L over K, K over F, etc. So, let me write it like this. Okay. So, my first claim is the following. It says that OL, AOL, this is equal to L times product over sigma I of sigma I B times OL for some integral ideal L of OL. Okay. So, L is my integral ideal. So, what does this mean? This means that so this is same as saying this is same as saying that AOL is contained in product sigma I B of OL. Okay. All right. Okay. So, that's one part of it, right. Now, so now we must show that L is the trivial ideal, right. And this is a standard trick that you will learn about showing how something is a trivial ideal. You show, you take something that's co-prime to that ideal, and then you show that that ideal is contained in that, right. So, for example, if you show that an integer divides a prime number, then and that integer is co-prime to that particular prime number, then that integer has to be 1, right. right. So, it is similar to that. So, what I am going to do now is I am going to take let B, okay, B is a bad notation, I think. Let C be an ideal of OK co-prime to L intersected with K. Okay. Plus we can always yeah, so L intersected K is some ideal, and we can always take C furthermore. So, here we use finiteness of class group. Furthermore, take C such that C times B is principal ideal. Okay. All right. Okay. So, then what we can show is that OL, A times OL, this contains product over sigma I of all these C's, well, not this kind of C, yeah, sorry, this C, right. So, you take the ideal generated by this, but this is of course equal to product over all sigma i's sigma I C times OL times product over all sigma i's sigma I B times OL. Okay. And hence L divides this ideal sigma I C times OL, okay. But it is co-prime to that. So, hence L is equal to 1, okay. So, that is a bit hurried, but yeah, that is the proof. You can try to go over this. So, let me just end with this remark that this uses finiteness of class group. Okay. All right. So, today we started the study of how ideals behave in extensions of number fields, and we will continue this study in the next lectures and even more than that. So, in particular we really want to find out what if you take a prime ideal in the smaller field, how it decomposes, how it factorizes, how its extension factorizes into product of prime ideals in the bigger field. So, that is our eventual goal for this study. Thank you.